For those folks, when we went offline on lecture 7, I started demoing this function read scale filter, or the radon demo. This guy here, radon demo impulse point. And so I'm just going to demo the code now for those of you who are working on the problem set and want to see the demo. So essentially, we take images of impulses, which are single pixel values, and we're just going to show you the original image. And we'll set a whole set of parameters for how to reconstruct that image by undersampling what we would regard as the optimal data or well-sampled data. So like any of these demos, you can run the entire thing. It clears everything, closes everything, and it runs the entire thing and puts up the output as windows. So on a Mac, you can just say command return, and it'll just run everything and make the figures. So let's just go through what the figures are. The original image is this. It's got single pixel dots when you go in, and you can take a look at any one of these pixels here. And they're displaced from the origin, in different directions. The first thing we look at is the parameters of our run. We're going to do every 1 degree projections through 180 degrees. This data signal to noise is set at 2. It says the recon kernel is hamming, but I would take that with a grain of salt. Here's the actual underlying true GL theta for this image, where we have the 180 projections every 1 degree, right? And so you have 180 values. If we want to make an even better data set than that, 180, let's go here. We can say we're gonna go every half a degree. Just run it again. And let's go back to our GL theta, which is here. We now have 360 values over the same 0 to 180. And this is the sinogram for this picture, okay? So this is the noise-free reconstruction of this. So you use inverse radon, or the iRadon function, as you'll see in the code, come down here. So the rad I is the raw data that we just looked at, the GL theta data. And then we just use iRadon on that data over different angles to give us the inverse radon transform, or what should be the original image back. So we can take a look and see if that's what it looks like. Here's the iRadon. This isn't the original image. This is what comes out of iRadon. And if we look at one of these boxes, you can see it blurs it a little bit. It started out as a single pixel, and then the inverse radon gives it this point spread function. Okay. It looks like there is no Hanning filter on here, because iRadon, we can put one on and see what that does. So you can just say Hanning, right? Do that, and then just run everything again. Oops, I guess I don't have, I just have a Hamming filter, okay. So let's go back, we'll change that to Hamming, since there is no Hanning filter. The Hamming filter, run it again. Okay, and get this guy out of the way. So let's go back to noise-free iRadon with that Hamming filter, and now this is what that box looks like. And so you can see it spreads it out even more than the default ROM-lock filter. Okay. Let's look at some, we're going to add noise to our data. And so we have the original GL theta, which is here. It's absolutely noise free. When you do iRadon, you get this noise free image with a point spread function. This is mainly governed by that Hamming filter. So let's add this noise onto this data, right? And so that's the raw noise is this. Geo theta plus scaled noise is this. And it looks like I've done some kind of filtering on that. And we can go back in and see what we've done here. So data peaks. So the scale, this is setting the signal to noise, or the noise value. And we've set it such that the signal to noise is whatever the largest data peak is, we'll set that signal to noise. So if we go in and look at our geo theta, you know, our largest data point is probably this one here, or, you know, where these three lines intersect here, we've got a large data point. But it's probably back there. We go here, yeah, that's probably our largest data point here. So the value of that data point here, which is 3, that's what we're going to use to determine our signal to noise. So we set the RMS of the background data such that when 3 is divided by that, it sets our signal to noise. Okay. We can try different smoothing functions. This, you know, let's do this one. This is smoothing in the theta direction. So on our sinogram, if we look at the sinogram and we say, okay, we want to smooth in this direction because we want to smooth out noise. We have big blank spaces, a lot of noise. We can set just a very simple, every 4 pixels in the raw data in the theta direction, we'll average them together. That's a trivial filter. We do that, and that gives us an image that looks like this, right? There's a trick here. If you want to look at, sorry, let's go, what was that? That's this image. So this is figure 7. We can say figure 7 in contrast. And that will let you adjust the contrast here. And so if we want to set the center down at 0 and look at more details of the noise, say 0.2 instead of 0.5. Now we start seeing those images we saw in the lecture where you see the smoothing in the theta direction causes a radial change in the essentially the spatial resolution of this image. Okay, and so you can try smoothing in the other direction as well if you want. Let's go in yeah. Now this is smoothing every second or every 4 pixels together along the detector direction. So every 4 detector elements will average them together. And this is the type of picture you get. Again, it changes the look of the picture entirely, right? You get this different background noise appearance, but we don't get this radially dependent smoothing in the noise field or the image for that matter. So you can try those different filters. And then if you want this figure that I've been moving out of the way every time, I just added, this wasn't in the original code, just to plot through the various boxes in the image. And so let's go back to smoothing in theta, right? We'll run that. And so what this code does here is it just starts a new figure and it plots through the image, right through the middle of the image. That's the central row of the image, 65, 33, and I think it's 9, which are the positions, right, of these dots. So we plot this row, this row, this row, and this row through the image, and just take a look at what that looks like. And that looks like this. Okay, and they're all plotted one on top of the other. We go in and take a look. Here's the 4 dots that are running up the central column of the image and their various widths. Right? And you can see it gets wider as we get out towards the outside because we applied that filter in theta. Okay, so that's the demo of this code. It's pretty simple, and have fun.